Hello to all, welcome back to Magic Tutorials for Chemistry. We will discuss about the valence bond theory, also called as VBT. So, according to this theory, the ligands are classified into three. The first one, strong ligands. That means strong ligands, they are good electron donors. They will donate the electrons and they will pair up the electron also. If in the coordination compound a strong ligand is present, then it will pair up the electrons. Electron pairing will take place, and the examples are carbonyl CO, cyanide Cn minus, and DMG. What is DMG? Dimethyl glyoxime. Dimethyl glyoxime. That is also a ligand, right? The second one, according to this theory, ligands are classified into strong ligands. The second one is the weak ligands. So, weak ligands, they are not good electron donors, they will not pair up the electrons. That means electron pairing will not take place, right. Which are the weak ligands now here? All the halogens, that is fluorine, chlorine, bromine, iodine, isothiocyanate, correct, and S2 minus. Mostly you will get for halogens, right. It has also considered ligands as average ligands. We will check that also. Average ligands means which will act as a strong ligand, which will act as a weak ligand also, correct. So, the examples are water, NH3, NO2, NO2 minus, OH minus, NO, correct. So, these are the average ligands. So, we are studying with VBT, valence bond theory. So, valence bond theory, according to this, the ligands are classified into three: strong ligands, weak ligands, and average ligands. Make a note of this. Okay. So, here one exception is there for NH3, that is for NH3. So, you have to remember this, the ligand NH3, it will behave as a strong ligand, correct. We have written it as an average ligand. According to VBT, NH3 is an average ligand, correct. So, when it is present in the complex, at that time how to identify whether NH3 is strong or weak, right. So, exceptions are there, like NH3 will behave as a strong ligand, it will behave as a strong ligand when it is attached to the metals such as cadmium, cobalt, iron and copper, correct. So, if these metals are present and NH3 is the ligand, at that time NH3 will behave as a strong ligand. With all other elements, with all other metals, NH3 will behave as a weak ligand. Yes. So, what does this theory explain? This theory helps us to find the hybridization, correct, hybridization. It helps us to find about the magnetic moment, magnetic moment, how to calculate, that is nu is equal to square root of n plus 2, and the unit for this is Bohr magneton, Bm, capital Bm, Bohr magneton. And what is n here, small n? It is a number of unpaired electrons. N is the number of unpaired electrons. So, if you put the value of n, suppose 2 unpaired electrons are there, put the value of n and find the value of magnetic moment. Next one is spin multiplicity. Spin multiplicity. So, the formula to find is 2s plus 1. To find the spin multiplicity, formula is 2s plus 1. Now, 2s plus 1, how to write the value of s? For s value in the formula, if one unpaired electron is there, then the value is half. If one unpaired electron is present, value is half. So, you will substitute this half value in place of s. If 2 unpaired electrons are there, then the value will be half plus half. 1 unpaired electron, the value is half, correct? So, substitute the value of s into this equation and find the spin multiplicity. The fourth property, that is magnetic property. Magnetic property. Magnetic property means whether the complex is diamagnetic or paramagnetic in nature. Now, how to identify? If there are unpaired electrons, it is paramagnetic in nature. The complex is paramagnetic. If there are all the electrons are paired up, then it is diamagnetic in nature, correct? So, this way you have to find the 4 properties according to VBT, valence bond theory. Let us take an example and find all the properties based on VBT. So, the first example, now we have learned the nomenclature. So, what will be the name of this complex? Potassium hexacyanoferrate, correct? Okay. So, according to VBT, explain the properties of this complex. That is a question given. So, first of all, what is the central atom here present? Fe, iron, right? So, write down the configuration for Fe. We have learnt in D block elements. So, it is organic configuration 3d6 4s2, correct? Okay. Now, find the oxidation state of the central metal atom. So, how to find the oxidation state? 4 into 1, potassium, the valence is 1, plus Fe, we do not know, so I will put it as x value, plus 6 into Cn, it is minus 1, equal to 0. So, the value of x will be 2, plus 2, correct? So, the oxidation number for iron is 2 plus. So, now write the configuration for Fe2 plus, it becomes organic configuration 3d6 4s0. 2 plus, that means you have to remove 2 electrons. So, now the configuration becomes 3d6 4s0, right? Okay. Now, we will draw this 3d6. D means how many orbitals? 5 orbitals, correct? So, 3d6 and 4s0, but still we will draw it. This is 4s and this will be 4p. 3d 4s 4p, right? Now, fill the electrons here. 3d6, so 6 electrons in 3d, 6 electrons in 3d, right? So, 1, 2, 3, 4, 5, 6. Fill one by one and then pairing up. Do not fill all together, correct? Okay. Now, check whether the ligand is strong or not. So, Cn, it is a strong ligand according to VBT. Cn, it is a strong ligand, so pairing will take place. So as Cn it is a strong ligand, pairing take place in 3D. We will draw the 4s as it is, 4p also, correct. So pairing will take place. Here already the electrons are paired up, this will pair up, this will also pair up, because the ligand is a strong ligand. So the pairing has taken place, right. Okay. Now how many ligands are there? 6 ligands are there, right. 6 ligands are there. So 6 orbitals we need. So 6 orbitals, where it is here, 1, 2, 3, 4, 5, 6. So what we are using here, D2, correct. 2 d orbitals we are using, 1 s we are using, and 3 p we are using, correct. So what is the hybridization here? D2 sp3. So we have found the first property of this complex according to VBT, that is D2 sp3 hybridization, correct. Okay. Now the second property is magnetic moment. So we have to find the value of mu, square root of n into n plus 2. What is n here? Number of unpaired electrons. Now are there any unpaired electrons here? No. So n value it is 0. Even if you substitute, the value of magnetic moment will be 0. The third property, spin multiplicity. So the formula is 2s plus 1, correct. Now how many unpaired electrons are there? 0. So value of s will be 0. So what is spin multiplicity? It is 1. Seeing that there are no unpaired electrons, don't write directly it as 0. Substitute that s value in 2s plus 1 formula and then write the spin multiplicity. And the fourth property, magnetic property, whether it is paramagnetic or diamagnetic. So here all the electrons are paired up, right. So it is diamagnetic in nature. It is diamagnetic in nature. Why? Because all the electrons are paired up, correct. So according to VBT, these questions can be asked. According to VBT, find the properties for this complex. So this is how you have to show the configurations and find all the properties, correct. Okay. One more thing I will tell you here is, here 3D is used, right. In the hybridization 3D is coming. At times in few examples you will be using 4D also. After 4s, 4p, 4D will come. Okay, at times in few examples you will be using 4D also. But here in hybridization we are getting 3D only, 3D. D2 is from 3D. So this complex is also called as inner orbital complex, correct. If 3D is used, it is also called as inner orbital complex. Suppose in other examples, as I said, 4D comes in the hybridization, correct, then it will be higher complex, or we can say outer orbital complex, outer orbital complex, outer orbital complex. So 3D is used means inner orbital complex, 4D is used means outer orbital complex, and inner orbital complex also called as low spin complexes, and outer orbital complex called as higher spin complexes. Let us take one more example. So the next example, NiCl4 2 minus, correct. Okay. Now find the properties according to VBT for this complex. So for nickel, What is the atomic number for nickel? It is 28. Correct. So, organic configuration 3D8 4s2. Correct. Nickel, it is a central metal atom. We will write the configuration for that 3D8 4s2. Now, for nickel, find the oxidation state of nickel here. So, how you will find nickel? It is X value 4 minus 1 4 Cl. Cl it is minus 1 is equal to charge is given. So, minus 2. Correct. So, if you find the value of X, it becomes 2. So, nickel plus 2. So, what is the configuration for nickel plus 2? Organic configuration 3D8 4s0. 3D8 4s0. Right. Okay. Now, draw it, the orbitals of D. 1, 2, 3, 4. This is 4s, this is 4p. So, 3d, 4s, 4p. Right. Again I will draw. Okay, let us fill this first. So, 3d8 electrons. So, fill it 1, 1, 1 first. 1, 2, 3, 4, 5, 6, 7, 8. 4s, it is nothing, no electrons. 4p also no electrons. Now, what you will check here? You have to check whether the ligand here, it is strong or a weak ligand. So, Cl minus, it is a weak ligand. So, pairing of electrons will not take place. It will remain as it is. Correct. So, this will remain as it is because the ligand is a weak ligand. So, pairing will not take place. Correct. So, as it is you can draw or let it be the same. Now, how many ligands are there? 4 ligands are there, right? 4 ligands, it needs the empty orbital. So, 1, second ligand, third and fourth. So, which orbitals we are using? We are using 1s and p3. 1s and p 1, 2, 3. So, what is the hybridization here? sp3. sp3 is the hybridization. Correct? Okay. Second one, how many unpaired electrons are there? We need to find the value of nu, n into n plus 2. Correct? N is the number of unpaired electrons. How many unpaired electrons are there? 1 and 2. 2 unpaired electrons are there. 2 plus 2. Right? So, square root of 2 into 4. Correct? That is equal to 4 2s are 8. So, square root of 8 we need to find here. So, square root of 8, that is 2.8. So, magnetic moment value is 2.8 Bohr magneton. Next, spin multiplicity 2s plus 1. So, how many unpaired electrons are there? 2 unpaired electrons are there. So, 2 unpaired electrons means it will be half plus half 1. So, 2 into s value is 1 plus 1. So, what is spin multiplicity? 3. So, spin multiplicity is 3 and the last property, that is whether it is paramagnetic or diamagnetic. So, here we can see unpaired electrons are there. So, it is paramagnetic in nature. Fine. So, this way any complex can be given. You can find the properties according to VBT. Let us discuss about the limitations of valence bond theory. So, this theory could not explain about the color of the complexes. What was the color of the complexes was not explained by this theory. Second is about the stability. The stability of the complex was not explained. Correct? Whether the complex is stable or not. it does not distinguish about the weak and the strong ligands. It does not distinguish for the weak and strong ligands. Fourth one, the experimental value and the calculated value. Experimental value and the theoretical value or the calculated value for magnetic moment do not coincide. Do not coincide. It is not coinciding, means it is not the same. Next, it did not explain about the geometry of the complex. It did not explain about the geometry, whether the geometry is this octahedral or tetrahedral, right. Then it does not give explanation that why some complexes are having high spin and why some complexes they are having low spin. Correct, as I told you this point earlier also, if they use 3D, d orbitals of 3D for hybridization, then it is inner orbital complex, okay, also called as low spin complexes. Correct. If in the hybridization 4D orbital is used, then it is outer orbital complex. It can also be called as high spin complex. So why it is like this? For few compounds it is low spin, for few compounds it is high spin, was not explained by VBT.